fuel cells. We'll also be looking at galvanic versus dry cells, and in the latter half of this video we'll also look at corrosion, how the redox reaction that we've been learning so far in this series for electrochemistry will affect corrosion, whether that's helping it or whether it accelerates it. Now you may have heard that fuel cells power hydrogen powered vehicles, right, or hydrogen cars, that they're the next big thing for transportation methods, and they're promising because they have no release of gases that are environmentally destructive. Obviously we know of maybe like CH4, right, the methane, highly potent greenhouse gas, same with like nitrous oxide, or obviously the big one that we all know about, carbon dioxide, right? So hydrogen powered vehicles, rather than releasing these, it actually only releases water, okay, or water vapor. Obviously very clean. Now here are a few half reactions with their pertinent standard cell potentials or voltage values over here. Obviously these are all in volts, right? Volts, 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 volts. And like I said, we want our overall reaction to have what as a product? What I just say? Water vapor. So then what would the reactants need to be? Well, of course, for the law of conservation of mass to stand true, there has to be hydrogens on this side and there has to be oxygens on this side as well. So let's put our oxygens, okay, and let's put our hydrogens, and we know that they cannot exist just by themselves, or they are diatomic molecules because of Hofbrinkel, so we have to be putting a 2 here and a 2 here. Now here's the thing, if there's 2 oxygens on this side, there has to be 2 oxygens on that side, so let's quickly balance it out. This messes up our hydrogen, so let's put a 2 in front of there. Now these half reactions here, you gotta pick which one you want to be using in order to create our fuel cell that releases just this water vapor, okay? So which one do you think we're going to be using? 1, 2, 3, or 4? What do you think? Maybe pause the video and try to think about this for a second. So if you selected this one, that would be incorrect. If you selected this one, also be incorrect. And if you selected this one, this would also be incorrect. The reason why all of these got X'd out, because we have hydrogen peroxide here, we have hydrogen peroxide here, and we have hydroxides over here, right? We're just only looking for these kind of ingredients, okay? So obviously the only thing that really makes sense is going to be this second one, okay? So let's write it out, and obviously we can tell based on that reaction over there that it is going to be cathode end, also known as a reduction half reaction, because we have this electron on the reactant side, okay? So obviously reduction and not oxidation. If it was oxidation, the electrons would be on the product side because it's being lost, it's being released. So let's put this all the way down over here. So again, this was all going to be summed up, so I'll just put a little dividing line over there, and the top portion here is going to be the reduction half reaction, and I'm just going to copy exactly what I see. Don't worry about the states right now. So if this is our reduction half reaction, we're missing the top one up here. We got to have an oxidation half reaction as well, right? We always need 2. So we have oxygen over here, both on the reactant side. So obviously this one is covered, but we also need hydrogens, right? Because we have hydrogen down here, so there's got to be hydrogen maybe up here in our oxidation half reaction, okay? So let's put maybe a hydrogen. Now our H2O here down at the overall reaction needs to stay, okay? And that's probably came from this reduction half reaction, so this one's gotta stay as well. So we have to get rid of some things. We have to get rid of this one and this one because obviously they're not down here. So maybe we can be putting our 4 H pluses on this side and our 4 electrons also on this side, so that eventually this and this can cancel out and eventually this and this can cancel out. Here's the problem though, we have 2 hydrogens here, we have 4 hydrogens here, so it really doesn't make sense. We may have to get rid of this 4s over here and be putting 2s. Let me explain why. Because if you have 2 H pluses over here, that means there's going to be a +2 on this side, which means instead of 4 electrons, we should actually just be putting 2 electrons, okay? Because obviously the 2 minus a 2 here will give us the neutrality, just like the left side is. Now, what does this mean regarding our addition of these reactions to produce our overall reaction? Well, we have to multiply this whole thing here, by 2. That way, we have 2 H2s. This one goes away. And you get a 4H plus. And this one too also goes away. You get those 4 electrons. So let's cancel them out. Okay, so this cancels out with this. This cancels out with this. So what do we have on the reactant side? We have our 2H2 and our O2 over here. And the only thing we have left on the product side is our 2H2O, as we see over there. Now it's important to note our standard cell potentials. Okay, we've already established in this reaction here that we've got from here that the E to naught, or the E standard, is 1.23 volts. And of course this is the reduction, or the cathode end, right? The cathode. Okay, this one here would be the anode end, right, for the oxidation. So what would this E standard be? It's not written over here, but you should already see the video link in the description if you've watched this video already. If not, please watch it. It's a prerequisite to this video. What the E standard value is when you have just our standard hydrogens reduction potential reaction. You remember what value it was? Hopefully remember that it was 0, okay? Because remember, the hydrogens can act as an oxidizing agent and a reducing agent. Again, see that video, please. So we know that the formula, right, is going for the total cell standard potential is going to be our cathode minus the anode voltage. So our cathode minus the anode voltage. So we just end up getting 1.23 volts. So the example we just did was a proton exchange membrane fuel cell, the most basic one that we have on the market. Like I said, the PEM, okay? But there's another type of PEM fuel cell, also known as an alkaline fuel cell, okay? So I want you to do the same thing, okay? How does it relate to redox? Okay, pretty much what we just did. Find out the anode, find out the cathode, the standard cell potentials, subtract them, find the difference, and tell me what it is. But also derive how we got the overall reaction. Let me give you a head start, and then I want you to do the rest on your own. Okay, so again, we want our overall reaction to be this. Okay, it's got to produce our H2O. And of course, our reactants needs to be our oxygen and our hydrogens. I'm going to be giving you a little hint here. We're going to be using this one, okay? We're going to be using this one. That's what is used in an alkaline fuel cell, okay? This is one of the reduction half reactions. So our O2, our 2H2O, our 4 electrons, yielding 4 hydroxides. And of course, you can tell that this here represents a reduction. So I'll be putting here reduction half reaction, obviously known as a cathode. So what would our oxidation half reaction be? Well, we don't have to worry about our oxygens because this oxygen here is already down here, okay? But we need a hydrogen, our H2, okay? The diatomic molecule of it, okay? It's not over here, which means this H2 must be somewhere up there, okay? It's on the reactant side, so let's put an H2 somewhere here. Now, how about our product side? Well, we can see that there's H2O here, okay? But as you can see, there is no H2O in this reduction half reaction, which means the H2O must have come up from up here. Can you do the rest on your own? Give it a try. So hopefully you've tried it out, okay? Obviously, we don't want this hydroxide over here, okay? Because we don't see it anywhere down here, which means there must be some hydroxides on this side, and then at one point we'll cancel that out and cancel that one out together. So let's put our hydroxides over here. Now, there's 4 hydroxides here. Maybe we should be putting 4 hydroxides over there. Now, if there's a 4 minus charge on the left side, there should be a 4 minus charge on the right side, which is actually going to be okay because we actually want to get rid of this 4 electrons anyway, okay? And the only way we can do that is obviously having it on the product side, because this one over here is on the reactant side. So let's be putting 4 electrons over there. So now we have -4 and -4. Also important to note that we didn't balance it down here properly. So we have our O2, there's 2 oxygens, there's only, how many over here? There's only 1, so we're going to be putting 2. Okay, so now we have 2 oxygens on this side as well. Okay, but now we have 4 hydrogens, there's only 2 here, so let's be putting a 2 over there. Does this change what we need to do up here? Absolutely, we have to be putting a 2 H2O up there. So now we have 2 oxygens on this side. We actually have 4 on this side. Okay, so we made a mistake. So let's change this one to the 2 OH minus. Okay, but that means if this is 2 minus, this side also has to be 2 minus. So let's change this one too. Now we have 2 electrons. As you can see, we have 4 hydrogens on the right side. We have 4 on this side as well. So now we have to multiply everything, whole thing here, by 2. So let's multiply everything here by 2. So then this changes to 4 OH minus. This one gets a 2 as a coefficient, and this one changes to a 4, and this one changes to a 4 as well. Okay, so now that we've done that, let's cancel out what we need to cancel out. This one goes away with this one goes away with this one, and this one goes away with this one. Did we end up getting what we needed? Beautiful, look at this. O2, O2, 2H2, 2H2, 2H2O, 2H2O. We are good. Now let's do our standard cell potential. Obviously this one here is already given here. It's 0.40 volts. How about this one up here? Apologies, I didn't give it up here, okay? And it's not written anywhere else. Hopefully you Googled it or had a chart, an elongated chart that has that value. I can just tell you right now that the E standard is -0.83. Okay, so we have our reductions, cathode minus the anodes. So it'll be 0.40 minus -0.83. What do we get for our total? It ends up becoming 1.23. Coincidence? I think not. It's the exact same total standard potential as the previous example of 1.23 volts. It is the same overall reaction. Let's tackle this question over here. Okay, what is a Daniell cell and a dry cell? If you don't know what a Daniell cell is, please see the video link in the description where we go into in-depth explanation and analysis about this. Daniell cell is pretty much a galvanic cell, and the example we used in that video was that the anode for a Daniell cell was zinc, a very reactive, but not reactive enough to hold and handle, but a lot more reactive than the particular cathode. And in this case, the cathode would be copper. Okay, so that's the one that we used in the previous video. Now a dry cell, however, though, the anode, still zinc, reactive, but the cathode uses graphite, okay, which is just like carbon, allotropes of carbon. If you don't know what allotropes are, see the video link in the description. Also for a Daniell cell, we use aqueous solutions in a salt bridge. Again, the video in this playlist about the Daniell cell, we went over this in detail. But in a dry cell, we just use an electrolyte paste. Hence the term dry. Now, let's answer this question. What is rusting? Okay, so rusting, you probably think of iron, right? Oxidation of iron. And that's absolutely correct. Okay, so corrosion being reacted with oxygen give us the term rusting, okay? In the presence of oxygen. Now in terms of its half reactions, how is it similar to the fuel cell concept? Well, the first reaction that we can look at is Fe. That's solid, obviously. It's a metal. Most metals are. So this is the first one. It has an E standard of 0.45. What do you think this one is? Is this the oxidation half reaction or the reduction half reaction? Obviously, it is the oxidation half reaction because the electrons are on the product side. Okay, so I'll just put here oxy half. And then the reduction half is oxygen, and obviously oxygen is gaseous, and water. This is why in humid conditions it can be quite a problem when we deal with rusting. And let's have 4 electrons here and yields 4 hydroxides. Obviously hydroxides are aqueous, and E standard is going to be 0.40. Okay, again, these are in volts. So what do we get for overall reaction? Okay, so overall we have 2Fe plus oxygen gas plus 2 waters, 2 Fe ions, and 4 hydroxides. So just like a fuel cell, works the same way. It undergoes redox, and we have to use our terms oxidation half reaction and redox half reaction and reduction half reactions. Find the difference between the two with our cathodes here minus the anodes here regarding these voltages, and then you get the overall voltage. So rusting, like fuel cells, all are related to redox. Now, is it combustion? Well, this is our rusting. How about our hydrogen power reaction? Remember, it was just H2O and oxygen and 2H2. Is there combustion going on over here? What do you think compared to this one down here? Hopefully you remember from your junior grades that oxygen needs to be present for combustion to occur. Well, there is oxygen over here as well. So is this one here combustion? So hopefully you remember from your junior grades that combustion requires oxygen as a reactant, okay? Now it also needs to be releasing heat, okay? And we have a lot more energy here with these two as opposed to water, right? We obviously know water doesn't have much energy. Pretty obvious when we think about calories. So if we have a lot of energy here, the Chatelier's principle is going to drive it towards the right, okay? So that's going to be produced, so it's going to release a lot of energy in that direction. This is going to be an exothermic reaction, but obviously combustion doesn't just need oxygen, it also requires some sort of spark or a light, okay? So there needs to be a spark over here, but provided that that is present, what else are we missing? Spark, okay? We need oxygen, and there needs to be a release of an oxide, and obviously water is an oxide. Technically its name is dihydrogen monoxide. So does this reaction follow suit? Well, obviously it's reacting with oxygen. Let's assume we add a spark here. Is there a release of an oxide? No, there is a cation of iron, and there is a release of hydroxide, but hydroxide is not an oxide. And obviously when things rust, there is no release of energy. So this whole thing is not a combustion. Only this one is. The rusting process is too slow, with barely any negligible minimal amount of heat getting released. This last concept I want you to understand is about reactivity, okay? Explain why aluminum provides a cathodic protection against iron. Obviously we don't want iron to oxidize because, let's say in cars, if it oxidizes and rusts, this can become a problem when it comes to safety of maneuvering handleability. So if we cover that object, so let's say we have an object over here and we have iron in the middle and it's surrounded by aluminum. Aluminum is more reactive than iron. So here I'll just put low reactive. The aluminum here will react with any, these ones over here on the outsides, okay? These are all just, let's say, in humid conditions like water vapor, okay, or water molecules. And obviously there's other particulates around, like dust particles on the outside in the environment that can react with the aluminum as well. Less than air particles can do that. But regardless, we want a metal on the outside that is going to react with them, okay? So this would act like an oxidizer, and it helps protect the iron on the inside and not rust. Now let's say there is a kink in the armor over here, okay? So let's say there's a scratch or a crack. Now we have this iron being exposed. Okay, so if the iron is now exposed, it's still okay because the aluminum is going to be the one that is going to oxidize, act as an anode, whereas the iron still stays as the cathode. So the iron is not going to lose its electrons, rather the aluminum's electrons are going to get lost. The iron won't break down, rather the aluminum is going to break down because it is losing its electrons and gives it towards the iron. It is more reactive, okay? It is being oxidized, whereas this one here gets reduced. This is why the question is saying it provides as a cathode protection, okay? Obviously this here, if this one is being reduced, is the cathode. I'll just put here cathode. Whereas this one here gets oxidized. So it protects this cathode. Now this method may seem foolproof, but there is a con to having a metal as being extremely reactive, even though it benefits the hidden package on the inside like iron. Can you think of a reason why an increased reactivity metal like aluminum can be a con? I'll give you a hint. Has to do with cost. So pause the video, give it a thought. Alright, so hopefully remember from the previous section of this video, they need to be replaced often. If you have a metal on the outside that is not as reactive, doesn't have to be replaced as often, so it lowers the cost. Now that's a segue for your practice problem for your green questions of the day at the end of this video. Let's have a look. So these are the two green questions of the day. This here is the first question. It's separated into two parts. And this here is the second question, also divided into two parts. In order for you to solve this kind of question, please see the video link in the description where we went into detail about galvanic cell potential. You would need to have reviewed that in order to solve this question. Please give it a try for these questions on your own. Please pause the video and I'll be giving you the answer shortly. This is the answer to the first question in the two parts. I'll slowly scroll down. This is the answer to the second question. Also in two parts, I will slowly scroll down.